All right. So hello to everyone who's joined so far. We'll get started in just a moment. I love that the bat cracking there. It's
Yeah. That
really
was
great.
I actually did a bit of analysis of that, the vibrations, and yes,
It's
that's
really
the neat
cool.
one. And then that
Yeah,
that picture is the same one that's in back of me here.
right behind you. Yeah,
Yeah.
I see that. Well, as people come in, we can at least start the intro. So, welcome
Okay.
everyone. Thank you for logging on for this evening's program. My name is Matt Schumann. I am a programming librarian here at Cary. If you have any technology issues, please message me in the chat, and I can try to help. And this program is made possible by the generous donors of the Cary Library Foundation. So, with us tonight is Alan Nathan. He's a professor emeritus of physics at the University of Illinois. And after a long career doing experimental nuclear and particle physics, he now devotes his efforts to the physics of baseball. He's written many articles both for academic journals and online baseball publications. He has given numerous lectures to a variety of audiences, and he maintains an oft-visited website, baseball.physics.illinois.edu. I'll put that in the chat. And that many people have found to be a useful resource. He's interviewed regularly by the media and has consulted for various organizations, including the MLB, NCAA, USA Baseball, and several MLB clubs, as well as various technology companies. Now, please welcome Alan Nathan.
Okay, well, thanks, Matt, for inviting me. I changed the title a little bit, but it doesn't matter. I just make up the title anyway. Baseball and Physics, an intersection of passions. And if you ever want to contact me, there's my email address there, and follow me on Twitter/X. So those of you in this attending this are probably Red Sox fans, and hopefully some of you will recognize Ted Williams right here on the left, and that in his final swing as a major league ball player at Fenway Park, in which he hit a home run. And this picture here is Cabrera who just retired. I have this because it's kind of a neat picture of a broken bat and the bat just kind of vibrating there. I'll have a little more to say about that sort of thing. So actually, baseball and physics are not my only passions. I'm actually very interested in American history, and so since you're from Lexington, I wanted to point out two books that I've read in recent years. One about the beginning of the Revolutionary War is called American Spring, and the other is actually the first of a three-volume set on the American Revolution. The British are coming. So paying homage to Lexington, where the first shots were fired. They got there before they got to Concord. Okay, so more on the baseball physics connection. So I want to tell you, and this has nothing to do with anything, but I thought it would be kind of a fun introduction. Moe Berg was one of the most curious people ever to play the game of baseball. He was a Princeton grad. By the way, I'm wearing a Princeton shirt here. That's where I was a grad student. This was given to me by the Princeton baseball team in my recent visit there. He was a linguist. He spoke multiple languages. He was a journeyman catcher. He, at one point, actually played for the Red Sox. And during World War II, he was a spy. He was hired by the predecessor of the CIA. I can't remember what it's called. And he one of his jobs was to attend a wartime conference in somewhere in Switzerland, because Werner Heisenberg, who was a great quantum physicist, one of the inventors of quantum mechanics, was going to be there giving a talk. This is during World War II. And Heisenberg was believed to be the person leading the German program to build the atomic bomb. And Moe Berg was instructed to attend his lecture and then engage him in some discussion and try to figure out how far along their bomb program was. And if he felt that their program had progressed, up, probably faster than they expected, his job was to assassinate Heisenberg on the spot. Well, it actually never happened. Anyway, very curious fellow. So here's the little story from the New York Times, 1994. Einstein and Berg met. So Einstein says, Mr. Berg, you teach me baseball and I will teach you the theory of relativity. And then after a brief pause, Einstein goes on, no, we must not. You will learn relativity faster than I will learn baseball. And actually, that says a lot about the game of baseball. Baseball is a very complicated game, okay? If you ever tried, if you grew up with baseball, it may not seem so complicated. But if you ever tried to explain the game of baseball to, somebody from some foreign country, in Eastern Europe or somewhere where they're not playing baseball, I challenge you to try to do that. It's not so easy. All right. So the thing that got me started on the physics of baseball was this book, The Physics of Baseball by Robert Adair, Bob Adair, who became actually he passed away a few years ago. He was a Yale professor. He wrote the book in the early 1990s, and this is the third and last edition. He, as I said, he passed away, I think, in about 3 or 4 years ago. One of my quotes that I like to give from this book is, our goal is not to reform the game, but to understand it. And that says a lot about what physicists generally try to do. Although a lot of the work that I've done and the work that he did has practical applications, his goal in writing the book and doing research, and my own goal, is really similar to what other physicists do. They're just trying to understand it. The game itself has been played, for 150 years. The players pretty well know how to play the game, and we're just trying to understand from a physics point of view what they already intuitively understand. And my website that Matt referred to is also a pretty good resource. I try to keep it up to date. It's become a little cluttered, and here's that same picture again of Ted. Anyway, you're welcome to visit it, and I try to highlight current research on the front page of it. Okay, so here are the topics I'm going to cover. There are 4 of them, although there's a little dot there instead of a 4. How does a bat work and why is aluminum better? Flight of a baseball. I'll talk about the aerodynamic effects. The home run surge in Major League Baseball, and the question that always comes up, has the ball changed? Is it still changing? And then a little bit about analytics, separating signal from noise, and advanced batting metrics. All right, so let's move on. How does a bat work? So what you're seeing on the right is a high-speed video, 30,000 frames per second, of a ball hitting a steel plate. The ball was fired out of an air cannon at 120 miles an hour. And the first thing you notice, when the ball is in contact with the plate, that ball gets crushed. Okay, it kind of gets smaller, right? It flattens out on the flat plate. Second, and that's a very, very inefficient process. When the ball gets crushed, if you were to cut open a baseball, what you would find is basically a big ball of yarn. Okay, it's mostly yarn on the interior. And when that ball gets crushed, the fibers of the yarn are rubbing together, creating a lot of friction. And that's energy getting transferred from mechanical energy into heat. And as a result, when the ball bounces off that steel plate, it's lost a lot of speed. So if you look at this, you can sort of see that the ball is moving about half as fast after it hits the plate as it did before it hit the plate. And so the collision is very, very fast, typically of order of thousandths of a second, probably even a little bit less. The forces are huge. To be able to turn that ball around from one direction to the other in such a short amount of time requires very large forces, thousands of pounds. And as I said, the ball gets crushed, and that makes it very, very inefficient. Lots of energy gets dissipated. On the left, this is Giancarlo Stanton for the Evil Empire New York Yankees. And this is one of these great pictures of opportunity where you actually see the ball in contact with the bat. And notice that now, unlike the steel plate, the bat has a round surface, and you see that ball sort of is wrapping itself around the surface of the bat. Again, another indication of the very large forces involved and the inefficiency of the whole thing. Okay, despite the large forces involved, physics still works, okay? And it must work. And so in particular, there is a concept of physics known as conservation of momentum. Momentum must be conserved. So here is Brandon Crawford. This is from a few years ago, maybe even 10 years ago, played with the Giants, and he's bunting the ball. So notice, so what is the bat is exerting a force on the ball, changing the direction of the ball, okay? And Newton's laws of physics, of mechanics, says that the ball has to exert an equal and opposite force on the bat, and therefore the bat recoils backward. And there you see it recoiling backward. Now, the same thing happens to a much lesser extent when the bat is actually being swung. It's already moving in the forward direction. So it doesn't recoil back, but it does slow down considerably. So here you're seeing high-speed video of a batter hitting a slow-pitch softball. There's the ball floating in. And there are 3 points on the bat that are being tracked with the video. And the distance between those 2 points is a measure of how fast the bat is moving. And you see that after the ball-bat collision, those points are much, much closer together. So the bat didn't recoil back, but it slowed down. It's exactly the same physics involved. It's conservation of momentum. So the stationary bat recoils, the swinging bat slows down. So a question arises. So one of the most important things a batter can do is obviously make contact with the ball, but to hit the ball as hard as possible. And today the lingo is you want a high exit velocity. That's the speed of the ball just coming off the bat. So it doesn't matter whether you're trying to hit a home run or just trying to punch the ball through the infield. The faster it comes off the bat, the more likely, and I'll show you some slides on this later, the more likely it is you're going to get on base. So generically speaking, there are 3 ingredients to determining what that exit velocity is. And this is the only formula I'm going to show you in this talk, okay? You could actually talk about physics without a lot of formulas. Exit velocity, EV, is equal to this thing called Q here, which I'll talk about in a second, times the speed of the pitch, plus 1 plus Q times the speed of the bat. So pitch speed matters, bat speed matters, and this factor Q matters. This is a property of the ball and the bat that I'm going to call the collision efficiency. It's a measure of how efficient that ball-bat collision is. Now, before going into some detail about this collision efficiency, I just want to give you some typical numbers. For a typical ball-bat collision, typical of what happens in an actual game, Q is about 0.2, which means 1 plus Q is 1.2, okay? And so if I plug in some numbers, if I use 85 miles an hour for the pitch speed, now why 85, why not like 95? It's because what matters, whoops, hold on, somehow, okay, just a second. All right, let me go, okay. What matters is the pitch speed at home plate, and the ball slows down by about 7 or 8 or 9 miles an hour between release and home plate. So 85 is a good representation. And a 70 mile per hour bat speed, you plug those numbers into this and you get 101 miles an hour, which is sort of typical of a home run. A ball hit at an optimum launch angle at 101 miles an hour will travel just a bit under 400 feet. So that's probably a home run. Now, the other thing you want to notice is that because 1 plus Q appears in front of the bat speed and only Q appears in front of the pitch speed, the bat speed matters much more than the pitch speed in determining the exit velocity. So each mile per hour of bat speed is worth about an extra 6 feet on a long fly ball, whereas each mile per hour pitch speed is worth 6 times less than that, about 1 foot. And now, to some extent, you sort of are, if you've ever played the game, you know that already, or if you've ever observed the game, you know that if you hit a ball off a tee, where there is no pitch speed, you can still hit that ball a long way. Okay, the other extreme is try to bunt the ball where there's pitch speed but no bat speed, and you know the ball's not going to go very far. So intuitively, you knew that already. You may not have realized just how big an asymmetry it really is. All right, so what determines the exit velocity? I told you it's the pitch speed, bat speed, and Q. What does the Q depend on? It depends on two generic features of the ball-bat collision. One is the weight, and it's really the weight distribution of the bat. It really depends pretty much on the mass of the bat in the barrel of the bat. The handle doesn't count for very much at all. The collision occurs in the barrel, okay? And heavier is better. The heavier the bat, the less that bat is going to recoil. The lighter the bat is, the more it's going to recoil or slow down in the case of a swung bat. And that all represents energy that the ball transfers to the bat. So it represents energy lost to the ball. So heavier is better from the point of view of this collision efficiency. But of course, the bat has to be swung also, and that's going to affect the bat speed. And the heavier bat won't be swung as fast as the lighter bat. So there's some optimization involved with trying to optimize the exit velocity by adjusting the weight of the bat, which has opposite effects on this collision efficiency and the bat speed. The second factor is the thing I call the bounciness of the ball. The fact that this ball that you see here loses a big chunk of its energy when it collides due to the fact that the ball is being crushed and a lot of the energy is just converted into frictional heat. This bounciness has a technical name. It's called the coefficient of restitution. I'll be referring to that, or COR. A higher COR means a larger collision efficiency and greater exit velocity. And the bat matters also, and I'll get into that in a second too. And in other words, it matters what the ball is hitting, something like a rigid steel plate or the bat itself. Okay, I'll get into that. Okay, so more in the ball-bat collision. So I want to actually focus in on the issue about the bat mass. The collision efficiency depends on the bat mass. A heavier mass is better. And the question is this: the batter is holding the bat, right? So, he's gripping the bat. How much does the batter, his mass, the mass of his hands, the arms, or whatever, how much does that contribute to the mass of the bat that contributes to this slowing down of the bat when the ball hits it? Is there less recoil with a tighter grip or with a more massive batter? So here are the two extremes of batters in Major League Baseball. This is Aaron Judge for the Evil Empire. He's 6 foot, 6 or 7. And this is Jose Altuve for the Houston Astros, who's like 5'7". He's shorter than I am. And so suppose those two batters are both swinging the bat with the same bat speed. Who will hit the ball harder, Aaron Judge or Jose Altuve? Aaron Judge is a scrawny little guy. Altuve is a scrawny little guy, whereas Judge is this big, massive guy. With a more massive batter, again, equal mass bat speed, does the ball leave the bat faster? Does the batter muscle the ball? In which case, is going to get hit harder by Judge than Altuve? So these are questions I want to try to focus in on. And this is sort of a fun thing to kind of think about. There are two key points about the bat and the ball-bat collision that lead us in the direction of how to answer these questions. The first is the bat is not a rigid body. I'll show you in a second. And the ball-bat collision, as I've already said, is very, very fast. Okay, so let's focus in on those two things. All right, so here is some high-speed video. This is, I don't remember who it is, but it doesn't matter. Again, high-speed video, and the ball is hitting the bat on the sweet spot of the bat. And if you look closely, you can see the bat slow down after the collision. Nothing funny is happening. So this is not the picture I want you to focus in on. I want you to focus in on this one. Here, the batter is hitting the ball inside of the sweet spot. You see it's hit nearly on the label of the bat. And look at that bat vibrate. It's the vibrations, look in the hands, it almost knocks the bat out of his hand. Similarly, if the bat hits the ball on the outside of the bat initially moves in the opposite direction, but you get tremendous amount of vibration. That vibration is a reflection of the fact that the bat is not rigid, okay? It can vibrate. And if you've ever played the game, you know that when you don't hit the ball on the sweet spot of the bat, it stings, it hurts in your hands, okay? So the sweet spot is the place where you don't have any vibrations. It also is the thing that feels best to the batter. And as it will turn out, it also gives you the largest exit velocity, because energy that's transferred to the bat in the form of vibrations is energy that did not go back into the ball, so it reduces the exit velocity. Okay.
So I'm going to try to demonstrate to you the principle of the...
Pause this for a second. I prepared this during COVID because it was easier to do this giving talks over Zoom. So just pay attention. I want to demonstrate an important point here via this video. I hope you can all hear the audio. Whoops.
So I'm going to try to demonstrate to you the principle of the sweet spot of the bat. So you know, as we saw in the video, if the ball is hit on the sweet spot, you don't feel any vibrations. You don't see any vibrations off the sweet spot. You do feel the vibrations. If you played the game, you know that. Okay? So I have this bat. This is a regular old bat, and I've got this plastic cup scotch taped to the top of it. The only purpose of that plastic cup is to sort of amplify the sound of the vibration so you could hear it. So listen very carefully. The knob vibrates and takes the cup right along with it. So vibrations, hit kind of begin, vibrations. Okay? Now do the following. You can do this at home. It's not that hard. Okay? Just start here and slowly work your way down towards the barrel to get vibrations. No vibration. And vibrations again. Vibration. No vibration. This is the sweet spot of the bat.
Okay, so I'll skip this slide. It's not important. I wrote a very long academic kind of paper about this very topic. Okay, so now I want you to watch this. This is actually a rubber bat, and I use this rubber bat just because I'm using it to demonstrate the point. Okay, so that is my hand down here with a little ball on a stick, and I'm hitting the bottom of the bat, which is just hanging there. And I'm striking the bat, in the barrel end of the bat. Okay, and here's what I want you to look at. I want you to look at the motion at the top in the knob region. And what you should be able to see is that handle starts to move only after a noticeable delay after I initially struck the bat. Okay, it takes time. So what's happening is a little wave is produced at the impact point, and that wave ripples up the bat. It bounces off whatever is up there, the knob, if you're holding it, your hands, whatever, and it reflects back down again. And the point is that by the time the reflected wave has come back down to the impact location, by then the ball has already left the bat. So nothing on the handle under the bat could possibly matter as far as what happens to the ball. Literally, the ball doesn't even know that the other end of the bat is there. Okay? Nothing could matter. The knob doesn't matter. The handle, the batter's grip on the bat doesn't matter. So the batter could just as well drop the bat, let go of the bat just prior to impact, and it would have no effect on what happens to the ball. Now, if you're skeptical about that, you're right. You ought to be skeptical about it because it's seemingly very non-intuitive. But let me show you something very interesting. A Memorial Day weekend in 2012, I'm getting ready to go to bed at night, and a buddy of mine says to me this thing, did you see what happened today? Todd Frazier, who at the time was playing for the Cincinnati Reds, hit what is essentially a no-hands home run. At the time, the ball and bat are in contact. The top hand is totally off the bat, and the bottom hand is just barely hanging on at all. The ball traveled 385 feet for a home run. Giving you an example of exactly what I mean when I say the bat is grip doesn't matter, and literally he threw the bat at the ball. Okay, and the physics is very simple. Has to do with the vibrations of the bat and the fact that the collision is very, very fast. Okay. All right. So is there less recoil with a tighter grip? No. Does the ball leave the bat faster with a tighter grip? No. Does the batter muscle the ball despite what the announcers say on the TV broadcast? No. All right. The bat is essentially a free body on the very short time scale, like a thousandth of a second of the collision. So why is aluminum better? So wood bats are used in all of professional baseball, both Major League and minor league baseball. But outside the professional ranks, non-wood bats are mostly allowed in college play and high school play, little league. They're used because they actually are better hitting instrument. And the question is why? Well, there are a couple of reasons why you might expect that an aluminum bat has a different weight distribution, simply because an aluminum bat is hollow. Okay, and so a smaller fraction of the total weight of the bat is in the barrel of the bat than it is in a wood bat, which is a solid object. It's actually aluminum bat could be swung faster, so you get a higher bat speed. However, there's less weight in the barrel, so there's a lower collision efficiency. And so I don't know why this has died. So it's a net wash. Okay. So that's not the reason. What's the reason? The reason is this thing called the trampoline effect. And it's because the bat is hollow. So I'm going to skip this. So what happens is this. When the ball hits a wood bat, that wood bat is a solid object, and you could vibrate, you could bend the bat, but you can't compress that cylindrical surface. So basically all of the energy during the collision is taken up by compressing that ball. And that's the part of the collision that's very, very inefficient. So there's lots of energy loss. But an aluminum bat is hollow. So when the ball hits the aluminum bat, the surface of the bat, the actual surface of the bat itself can compress. And for reasons that are somewhat technical, and I'm not going to go into, that the energy that goes into compressing the wall of the aluminum bat is very efficiently returned back to the ball again. So there's less energy lost in the collision because the ball is not compressed enough. Some of that energy is taken up compressing the bat. Okay, and that's what's known as a trampoline effect. And why is it called that? You know, imagine bouncing up and down on the floor versus bouncing yourself up and down on a trampoline. The trampoline can give. Okay, just like the surface of an aluminum bat can give, and it gives and gives back to the ball again. And this is not, so that there's something called the ball bat coefficient of restitution, which is enhanced with an aluminum bat, and therefore you get higher exit velocities. You see the same effect in tennis, where the trampoline effect comes from the compressing of the strings of the racket. And you see it in drivers in golf, where they used to be called woods. They're not woods anymore. They used to be a solid piece of wood, like a solid wood bat. Now they're a hollow piece of metal, and you get a trampoline effect there. Okay, so it's not just baseball that has it. Okay, and that's why the aluminum bat is better. And so the quiz, to get a higher speed on your serve, a lot of people, their intuition tells them they want to tighten the strings. You want that to be a real tight collision, okay? The answer is you want to loosen the strings. You get more of a trampoline effect the more those strings give, okay? All right, now I want to turn to the second topic, the flight of the baseball, and I'm going to cover this mostly pretty quickly. There are three forces on the ball as it's traveling through the air. gravity, that's mg here, is pulling it down. The air drag, the fact that the ball has to push the air out of the way, is slowing the ball down. And if the ball is spinning, there is what is called the Magnus force on a spinning ball. It's the thing that makes the ball change direction. And if you want to know what direction it changes, if you look at the leading edge of the ball, the front of the ball as it's going through the air, the direction that ball is turning is the direction that force acts. So a ball that's hold on a second. I'm going to get a ball. If the ball is coming towards you, the ball has backspin on it, the leading edge is pointing up, and that there's an upward force that keeps the ball in the air longer because it's opposing gravity, so the ball will travel farther. A four-seam fastball has backspin on. A curveball has topspin, and the Magnus force on a curveball is downward in the same direction of gravity. And so a typical movement on a curveball is a downward movement. Okay. All right. Nowadays, there's a lot of technology in the ballpark that's used. This is the so-called StatCast system. It's a great tool for both doing baseball analytics and doing physics. And in particular, these cameras are tracking the baseball. They're tracking the pitch ball, the batted ball, the thrown ball. And there's a tremendous amount of really useful information, both for the game as well as for understanding the physics of the game. It's a camera-based system, measures the spin also, et cetera, et cetera, et cetera. So I want to tell you briefly about the difference between what I call a Physics 101 baseball and reality. So this is a famous home run. This is the home run that Barry Bonds hit back in 2007 that broke the all-time career home run record. And so we have actually tracking data. This is the actual trajectory of the ball. So I have a model that I created for the aerodynamics of a baseball that I adjusted, the various things associated with the drag and the Magnus in order to fit the data, okay? And once you have that, then you could start playing all kinds of interesting computer games. So for example, I could turn off all the aerodynamic effects, the drag and the Magnus force. I could say, all right, let's pretend this same ball, which traveled about 450-ish feet, suppose that were hit in a vacuum where there is no air. That same ball would have traveled close to 700 feet. So the drag, which is what slowed that ball down so that it only traveled 450 feet, that plays a huge role, okay? The backspin on the ball, which gives it lift, plays also a role, but not as big a role. So in this dash line calculation, I have turned off the drag that slows the ball down, but I've kept the Magnus force. And you see that it reduced the distance from 440-ish feet down to maybe 380 feet. So drag matters a lot. The lift or the Magnus force matters also, but not anywhere nearly as much as the drag. Okay, so I want to tell you various things that we've learned. Let's see. I'm showing you these things here. These are actual data, average data from Major League Baseball, showing you for a given range of launch angles, 25 to 30 degrees, how the batted ball distance plotted here on the y-axis depends on the exit velocity, okay? And you see, I'm showing you both at sea level and in Denver. Denver is, my screensaver keeps on doing stuff here. Denver is at a mile high above sea level, and there's less air, okay? And so there's less drag and the ball carries further, not a little further, a lot further, maybe 20 feet further, okay? But each mile per hour of exit velocity is worth somewhere between 5 and 6 feet. The other thing to note is if I look at a fixed exit velocity, if I look at how it depends on the launch angle, you see that this thing peaks at somewhere between 25 and 30 degrees. Very, very much unlike what it would be like in a vacuum. In a vacuum, the Physics 101 case, the distance would peak at at precisely 45 degrees. So the effect of the drag is to really reduce that considerably. So 25 to 30 degrees is the angle if you're trying to hit a home run. That's how you want to hit it. So what have we learned? So each additional mile per hour of exit velocity gives you about an additional 5 feet of carry. Okay. The effect of temperature, 10 degrees increase in temperature gives you about another 3 1/3 feet. And that's not a whole lot, but if you're trying to compare, a cold day in April to a hot day in August, where there might be a 50-degree swing in temperature, that's a lot. Altitude, each 1,000 feet is worth about another 6 feet. I'll skip that. Oh, wind is very important. A very, very modest 5 mile per hour wind blowing out will increase the distance by something like 18 feet. That's huge. Okay. And I'll skip that. A useful question is, how far can a fly ball travel? My estimate is if you look at the distribution of exit velocities in Major League Baseball from last year, they peak out at about 120 miles an hour. And if you were for balls hit at 30 degree, about the optimal launch angle. Sorry, for some reason my screen just keeps on timing out. You see that at 120 miles an hour, which is about the largest exit velocity, this ball travels about 500 feet. So that's about the longest fly ball that could be hit, assuming this 120 miles an hour, unaided by the wind or any other unusual atmospheric conditions. And if you look at Major League Baseball over the last few years, you see a handful of balls that were hit at close 500 feet or close to it. And there's a famous, if you've been to Fenway Park recently, there's a famous red seat. Here it is looking in. It's a long ways away. This is a ball. This is the seat where that Ted Williams hit this home run in 1946. And that this seat is about 30 feet above ground level. If the ball would have been free to travel the rest of the way and hit the ground, it would have traveled something like 537 feet. But this was wind aided. There was about a 20 mile per hour wind. Okay. Anyway, so there's my own rendition of the red seat home run at Fenway Park. All right, I want to turn on to the third topic. I want to talk about the home run surge in Major League Baseball. So what I'm showing you is the rate of home runs per ball in play. So in 2014, it was about 3%. About 3% of the balls that were put in play ended up as home runs. And then it started to increase. There was a decrease in 2018. It reached an all-time high in 2019, where representing something like a 70% increase between 2014 and 2019. And then it went back down again. It reached a low point in 2022. Between 2019 and 2022, there was about a 30% decrease. Then last year it went up again. And this last dot here, this is, literally hot off the press. This is based on the April data from this season. Looks like it's back down again. Okay, and the question is why? Okay, and that's the question I want to try to answer. Why all the changes? There are a lot of conspiracy theorists that talked, back in 2015, 16, 17, when things were on their way up, that the ball was juiced. And juiced usually means that this bounciness factor, is higher, okay? There's less energy lost when the ball hits the bat, higher coefficient of restitution, and that will result in a higher exit velocity. And Rawlings, the company that makes the baseballs, they know how to create baseballs with different coefficients of restitution. So there were, people were suspecting that some conspiracy between Rawlings and Major League Baseball that resulted in a higher coefficient of restitution. But you could test that coefficient of restitution in the lab, and that's ruled out. The other possible reasons are change in batter behavior. Batters are swinging harder. They're trying to hit more home runs by hitting by swinging harder. You'll get a higher exit velocity. They're altering the swing plane of the bat in order to achieve a more optimum launch angle. Remember, you want to get it 25 to 30 degrees. If you hit the ball hard, but it's going, straight back towards the pitcher, or even in the infield, you may get a hit, but you're not going to get a home run. And that turns out accounts for some of the changes. But much of the changes have to do with the reduced air drag on the ball. So for a given launch condition, exit velocity and launch angle, during the years where there was an increase in the number of home runs, the ball was actually carrying further. And that was confirmed both by in-game data from these tracking cameras as well as laboratory experiments. And that accounts for much of the changes. And so I'm going to skip talking any further about that, except to say that you could create a model and where the red points are the predicted number of home runs based on the model including what the exit velocities and launch angles were, compared with the actual number of home runs, and the fact that post 2019, the actual number was below the predicted number, means that the air drag actually increased during those years. You didn't get as many home runs as you would have predicted. So the effect of the ball, going through the air, the effect of the air drag has, been both a positive effect when things are on their way up and a negative effect when things are on their way down. Okay, I want to skip that. All right, the final topic I want to discuss is separating signal from the noise. This is not so much physics as it is analytics, but it gives you an idea about how people that are doing analytics for major league clubs are using what you might call advanced metrics to determine, how a particular player is doing. Okay. So the traditional metrics are outcome-based, meaning they're based on, the batter hits the ball, what happened? Did he get on base or not get on base? Did he hit a home run or not hit a home run? So batting average is an example, okay? It's outcome-based. Now, batting average is partly determined by skill. So, for example, if you hit the ball hard, you're going to increase your chances. But it's also partly determined by luck. A batter could hit the ball really hard right at a fielder, okay? And, he's not going to get on base. Or he could just totally muff the swing and hit this little weak grounder that he beats out for a hit, okay? So there's a lot of noise in addition to the skill. And the goal, really, of any analytics is try to separate the signal, which is what you're interested in. You want to know the skill level of the player. You want to separate that from the noise. So I want to give you an example. This is from last season. What I'm doing, each point here represents a particular player. And what I'm doing is, on the horizontal axis is the batting average of that player for the first half of the season. And the vertical axis is the batting average during the second half of the season. And they're correlated. Okay, this line sort of shows you that they're correlated. You see the points more or less follow that line, showing that if a batter hits well in the first half, he's going to hit well the second half. But there's a tremendous amount of scatter about that. The scatter, the signal is this line. The scatter is the noise. Over 60% of the variance of those points relative to this line is due to random noise. Oh, sorry, I said that wrong. If you look at the variation, the total variation among these different players in batting average, over 60% of that variation is due to noise. Only 40% of it is due to the actual signal, the skill level. Now, Okay, so the goal, so can we develop new metrics based on other characteristics of the batted ball? So for example, exit velocity. So do we want to reward players who have a high exit velocity, despite the fact that due to bad luck, they may not have gotten on base with that high exit velocity? So let me show you. This is, again, from last year. Hit probability, the probability of getting on base versus exit velocity. Once you're above about 80 miles an hour or so, it increases very, very rapidly. So it looks like exit velocity is a very good surrogate for hit probability or getting on base. So I want to apply the same kind of analysis to exit velocity as I did the batting average. So this is, again, each dot represents a player. I'm plotting exit speed in the first half of the season versus exit speed in the second half of the season. Again, the correlation line is here. Higher exit velocity in the first half, more or less results in higher exit velocity in the second half. But now you see those points are much more tightly clustered around that correlation line. And so now only 18% of this total variation is due to random noise. Okay. So exit speed seems to be a very reproducible skill. All right. So finally, I'm down to my last few slides. Things that keep me busy these days using ball flight data. You know, I told you I developed this model for calculating trajectories based on exit velocity, spin rate, and things like that. I'm always looking to improve that. I'm looking to develop a quantitative understanding of something called the seam shifted weight, which I never talked about in this talk. But for those of you who follow baseball closely, know that in addition to the spin on the ball causing it to change directions, the seams also play a role, and that's called the seam shifted weight. The seam shifted weight, for example, is what gives rise to the funny behavior of a knuckleball. Using bat tracking data, which is new in Major League Baseball this year, to try to improve my model for the ball-bat collision, and doing experiments to try to explain why some wood bats are better than other wood bats. We know why aluminum's better than wood, but why are some wood bats better than others? So feel free to contact me. You could reach me via email, follow me on Twitter/X, and thanks for listening, and go Red Sox. And that's me in my Red Sox uniform at the Red Sox fantasy camp in Fort Myers back a bunch of years ago. All right, I'm done and I'm ready to take your questions.
Thank you so much, Alan. That picture is great of you there.
Yeah.
Thank you for this wonderful presentation. It's super fascinating. If anybody has questions, please put them in the Q&A, or you can use the raise hand function, and I can enable you to talk. Maybe while people are typing their questions, I have one. Maybe it's like too simple of a question, but are you able to talk about maybe some of the physics of some of the ways that people cheat in baseball?
Oh. Yeah. So let me give you a relatively current example of that. I think it was 2 years ago, actually beginning 3 years ago, but really taking shape 2 years ago during the 2022 season. One of the things that this bat tracking cameras do is they tell you the spin on the pitch ball. And the more the pitcher is able to put spin on the ball, the more movement he's going to get. Whether it's left-right movement, up-down movement, or somewhere in between. And it was noticed that a lot of if you're monitoring this over time, there was a marked increase in the spin rate of the pitch ball, leading to more movement. And it was suspected that pitchers were applying something to their fingers, which then, some sticky substance to the fingers. So the way the pitcher puts spin on the ball is through the friction between his fingers and the surface of the ball. And by putting some sticky substance on his fingers or on the ball, you can get more friction and therefore more spin. And so Major League Baseball decided they wanted to crack down on that. So that's cheating. Okay, you're not supposed to do that. And so Major League Baseball decided they really had to do something about that. And so they started inspecting pitchers. And it's amazing. You start looking, beginning roughly this time of year in 2022, you start looking at the spin rate on pitch balls, and they started to decrease again. And you may notice if you're watching a game on TV, at the end of an inning, the pitcher will go up to the home plate umpire, and the umpire will look at his glove and, look at his hands. And they don't do that every inning, but they do that several times during the game. And thus far, I don't think very many people have been caught doing that kind of cheating. That's a good example of cheating.
Thank you. We do have a number of questions that have come in, so I'll get to those. There's also a comment. Remember, those of us who love the evil empire have 27 reasons to smile. But
all right,
so
fair enough.
All right, so the first question is, why are the tops of bats hollowed out, and when did that start?
Oh, okay, that's a good question. It's in a sense it's useless weight. Okay, the weight. So you're trying to, that weight is very far from the hand. So weight added near the end of the bat, near the barrel end of the bat, tends to result in a slower swing speed. So, again, it's an optimization thing. Reducing the weight of the bat in the barrel of the bat allows you to get a higher bat speed, but it reduces a little bit the collision efficiency. However, it does have another important effect that I didn't emphasize, but I will now. Namely, by reducing the amount of weight, you might probably sacrifice a little bit of exit velocity by doing that, but you have better bat control. And so better bat control means once you have begun your swing, you're better able to adjust that swing as you gather more information about what the pitch is doing as it approaches you. You're able to hold up or make whatever adjustments you need. And batters seem to prefer that. Certainly college players, by using aluminum bats, do suffer a little bit from exit velocity by having less weight in the barrel of the bat, but they prefer to do that in order to have better bat control. And it allows you to wait a little bit longer in the pitch. So when you have a 95 mile per hour fastball or higher, you can use all the help you can get when trying to control the bat. It's a good question.
Yeah. Mukesh has their hand raised, but they also typed a question in the chat. They were next, but Mukesh, you should be able to unmute yourself. And sorry if I'm mispronouncing your name as well.
It's pronounced correctly. Thank you for the presentation, Alan.
Thank you.
I had a bunch of questions. The first was if you can talk a little bit more about the seam shifted wake and how it affects the trajectory of the knuckleball. And second was that how would gripping the bat a bit lower, like with one hand close to the knob and the other one a bit lower, would it affect the bat control and exit velo with the same bat swing speed?
Let's see. Let me get to the second question first. Do you want the grip to be closer to the barrel of the bat? Is that what you want?
So rather than both hands being close together, you increase the distance between the hands that one hand is closer to the knob and the other is closer to the barrel.
Yeah. Interesting question. I haven't really studied that. And there aren't too many batters in the history of baseball that have done that. But one very famous one did that. Ty Cobb actually did that. And I think you probably get better bat control that way. I'm not sure you get a better bat speed, but you certainly have a better bat control. A lot of times when batters have two strikes on them, then they definitely want to have better bat control. So they usually cut down on their swing. They're not swinging quite as fast because the faster you swing, the less able you are to control where that bat is going. But they do what is known as choking up on the bat, where they're putting their hands further from the knob, effectively shortening the bat, okay, making it easier to swing, okay, and therefore easier to control. And they do that with 2 strikes, so they have better control over what their goal is. They don't want to strike out, okay? They want to be able to have that neat ball. And you can, even if it means a bit lower exit speed than you would get if you didn't choke up. Now, seam shifted wake, yeah, I don't want to go there. That's a long topic. And if you want to send me an email, I'd be happy to point you in the direction of interesting stuff people have written about it. I've written some stuff about it myself. But it's a long topic, so I purposely avoided it for this talk.
So thank you, Lokesh.
Sure.
Next question is why did the ball have less drag around 2019? I forget if you had already said that.
Okay, no, that is actually a good question, and I wish I could give you a definitive answer, but I can't. Okay, so let me just say. When beginning in 2017, when people really started to, when all these conspiracy theories about altering the ball really first were really becoming rather frequent, Major League Baseball was a little bit worried about the bad publicity that they were getting as a result of this. So they formed a committee of mostly academic type people to study this problem, to really go into detail, to try to understand why there was an increase in home runs. And I actually chaired the committee, okay? So that was my first consulting gig with Major League Baseball. So I know all about it. And it was actually a surprise to us when we first looked into it. Nobody suspected that it was this drag issue that was causing the increase in home runs. No one had even given that any thought prior to this, but it became apparent to us very early in our studies that this was the primary reason for the increase in home runs between 2014 and 2019, and the primary reason for the decrease in home runs since then. So so here's what you need to know: the air drag on the ball depends on things that we certainly know about. The air density, we know all about the air density. You can measure the temperature, the pressure, and all that. We know about all that. But there's a property of the ball. The ball has to push the air out of the way. And some of the air actually slides around the ball. And so it doesn't have to push all the air out of the way, because some of it can sort of slide around the ball. And the more easy it is to slide around the ball, the less drag there is. That's why people, automobile makers spend a lot of money putting their cars in wind tunnel to reduce the amount of drag, to, build the shape of the car in such a way. Airplane wings are another example. So the ball is more or less a sphere, and, it's pretty much smooth leather with these red stitches. Okay. You see the stitches, and it's the stitches that are doing it. If the ball were a perfect sphere without the stitches, there would be drag on it. There'd probably be more drag on it, but it wouldn't be. It would be very easy to control that drag because the ball is very smooth. One of the things that we got to do on this committee was we visited the facility where the baseballs are made. The baseballs for Major League Baseball are made. It's in Costa Rica. So I got to go to Costa Rica, and I had a day-long tour of the factory. And most of the construction of the baseball, the winding of the yarn, for example, is all done by machine. The one thing that's not done by machine is the sewing of the 2 pieces of leather to sew these stitches on, to sew the whole thing together. It's all done by hand. And it's the most amazing thing you ever saw. There's a room full of maybe 200 people who all day long are stitching the baseballs, okay, with this motion, and then, they're taking breaks every now and then just so they won't get repetitive motion problems. But this is all done by hand. They're all inspected, but you could take two different Major League Baseballs and you could see noticeable differences in the seam height. And this seam height affects the drag on the ball. When the seam height is high, there's more drag. When it's low, there's less drag. But it's more than just the seam height. There are very, if you look at these seams carefully, there are little holes here, and there's funny little pattern. It's a V kind of pattern. And that all affects the drag in ways that we really don't have a handle on yet. So there was so we discovered the following two interesting facts. Number one, there is a change in the average drag on the baseball from one year to the next that gave rise to the number of changes in home runs. But number two, within a given year, there is a lot of ball-to-ball variation in the drag. And that ball-to-ball variation on the drag is greater than the year-to-year variation. So there's more variation within a given year, sometimes within a given game, than there is from one year to the other. And none of these things are quantitative. I think we understand qualitatively it has to do with the seams, but quantitatively we haven't been able to figure that out yet. And that's a very good question.
Do you have time for a couple more?
Sure.
Okay. Somebody asked, why is using a corked bat cheating?
Because it is. Okay. So let me tell you about a cork bat. The idea of a cork bat is that the batter, hold on a second. I'm getting my bat here. This is that rubber bat that you saw in the video. The idea of a cork bat is you want to reduce, the idea is to reduce the amount of weight in the bat, in the barrel of the bat. And as I've already said with regard to cupping the bat, if you're trying to get a high exit velocity, that's a losing proposition. Okay, can you still see me?
Yeah.
Because my screen keeps on timing out. Nevertheless, by reducing the weight of the bat in the barrel of the bat, you are able to have better bat control. So there's a reason why batters want to do that. And the idea is you drill a hole maybe 1 inch in diameter and about 1 foot deep into the bat. And in doing that, you're reducing the weight of the bat by a couple of ounces right in the barrel of the bat, where it matters most. So you're able to get a higher swing speed, but you have less collision efficiency. It's sort of a losing proposition for exit velocity, but you do have better bat control. The cork, you fill it with cork. The only reason why the cork doesn't do anything other than hide the fact that you've done this illegal thing. You paint over it so they don't know it's there. And there was a famous incident that happened way back I think it was in 2003, where Sammy Sosa for the Cubs was caught using a cork bat. The bat broke and out flew the cork. I spent the next 2 days constantly on the phone with one reporter or another answering questions about cork bats. But yeah, a cork bat is actually a useful thing if you're trying to make good contact. It's not a useful thing if you're trying to hit a home run.
Interesting. Are there types of wood that are better than others for bats?
That's a good question. And you want a hardwood. You want a wood that has about the right density, because the shape of the bat is pretty well, there are small variations, but it's pretty much fixed. So you want a bat, so that places some limitations, and you want a wood that's hard so it doesn't break very easily. You don't want the bat to dent. So, nowadays there are 3 types, back 20 years ago, mountain ash was the primary wood that's used. But mountain ash, there's the emerald ash borer that is destroying in Pennsylvania and New York, where the wood is actually grown, destroying the crop of wood. And so people have switched to maple. And I think maple probably is the majority of bats now in Major League Baseball. And birch is another one. And there are others, beech, European beech or something is another one. And there may be others. But as far as I can tell, they all perform about the same. I don't think there's any. They may have they may be different in terms of how easy they are to break. But in terms of what matters most, which is exit velocity, or yeah, they're all very, very similar. There might be small differences, but you have to go to a lot of effort to find those small differences.
Another person had a question. There's a StatCast statistic that called expected batting average. What are the factors of that?
I'm not sure exactly. It probably has to do with exit velocity and launch angle. So, you know, but I don't know what other variables are included. It may also include the direction the ball is hit. But so you can imagine what they do is they've got a huge database where they've got whatever variables you want to consider: exit velocity, launch angle, maybe the direction, the spray angle. And you could just look at thousands of hits, batted balls with those characteristics. And in this three-dimensional space of exit velocity, launch angle, spray angle, you could find what is the probability that there will be a hit. And that is the expected batting average if you have it, you know. So it's expected in the sense that all the other hitters before you, you know, hit it with that, when they hit with those parameters, they got on base with that probability. So, so in detail, I don't know what's included, but almost surely exit velocity, almost surely launch angle. I don't know if spray angle is also included. I'm just not sure. You can go to the StatCast website, by the way, and get a precise answer to that.
Okay. Is there any strategy a batter should use when bunting?
Oh my goodness.
Maybe that can be the last question too.
Um,
Unless if you don't have a good answer.
Yeah, the answer is probably yes, but I don't know what the answer. I mean, I don't know what that strategy is. I mean, yeah, I'd have to think about it, and I'm not sure I could give you a very good answer anyway. I'm sure there's a strategy, but I just don't know what it is.
Right. Maybe the last question could be, when you're talking about the effect of like wind on pitches and whatnot and the temperature and whatnot, are there certain markets or certain like parks that teams have like an advantage because like they're indoor versus an outdoor park, or temperature is like, you know, like Arizona is always going to be
Right.
You know,
Okay, so there are two things. Well, so it all has to do with air density. So for example, Denver, for the same reason why fly balls travel further in Denver, pitches, there's less movement on pitches in Denver for a given amount of spin on the ball. And it's the same reason. Both the air drag as well as the so-called Magnus force on the spinning ball is directly proportional to the air density. So Denver is a nightmare for pitchers, both because fly balls travel further and because pitches don't move as much. And pitches move more in warm weather than cold weather. So you get, I'm sorry, I said it exactly wrong. They move more in cold weather when the air is denser than they do in warm weather, where it's less dense. Now, you know, in Arizona, it gets pretty hot in the summer, you know, routinely over 100 degrees, but they're playing most of their games when it's that temperature with the roof closed. So it's temperature controlled. But yeah, I mean, you know, there are, you know, you go to Chicago in early April to watch a game, and it could be pretty cold. And wind plays a role also. So wind can affect the trajectory of a pitch ball, just like it affects the trajectory of a batted ball. The effects are not, I mean, you'd have to have a pretty high wind to have too much of an effect because the ball's not traveling over very much distance. But you know, you can get an extra inch or two of break on a ball if you've got a stiff side wind.
Well, that makes sense. Thank you for taking all this time to answer questions and take time out of your evening to present this.
Yeah, no problem.
Really fascinating talk tonight. Thanks to everyone who was here and contributed tons of questions. This program was recorded and will be on the library's YouTube channel in the next coming days. But thank you so much again, Alan. This was awesome.
Okay, my pleasure. And yeah, enjoy the evening.
All right,
Bye-bye.
have a good night, everyone.
Bye.